You know how a self-driving car can spot a pedestrian? Or how your phone camera puts those funny filters on your face, like instantly? Well, it all comes down to this really foundational piece of AI called object detection. It's the ability for a computer to not just see a picture, but to get what's in it and where everything is. And today, we're going to dig into a breakthrough that completely changed the game.
For a while now, AI has been pretty decent at this. A network can look at a photo like this one and go, okay, that's a bus, and right there in front, that's a bicycle. And that is amazing. But for the longest time, there was this one huge catch, a fundamental problem that was holding AI back from being really, truly useful out in the real world.
Because let's be real, identifying a bus in a static photo is one thing, but identifying that bus and every other car and every pedestrian and every traffic light while you're cruising down the highway, that's a whole different ballgame. The real challenge wasn't just about being right, it was about being right now. Okay, so let's get into this core problem. In the world of AI, you often have to make a choice. And for years, researchers working on object detection were just plain stuck in this classic engineering dilemma. It was a really brutal trade-off. The systems that were incredibly accurate, the ones that could find things with pinpoint precision, were also painfully slow. And on the flip side, the systems that were fast enough for real-time video, well, they just weren't that accurate. They'd miss things, they'd get stuff wrong, and for a lot of applications, that's a deal breaker. And this table right here, it shows you that trade-off perfectly. You had faster RCNN, which was the king of accuracy at 73.2%, a fantastic score. But look at its speed, only 7 frames per second. Then you had YOLO, which was way faster at 45 FPS, but its accuracy dropped by almost 10 whole points. So you were stuck. You had to pick your poison. Did you want it to be right, or did you want it to be fast? Let's just park on that number for a second. 7 frames per second. That is slower than an old black and white movie. For a self-driving car that needs to make a split-second decision, maybe about a kid chasing a ball into the street, 7 FPS is an eternity. It's just way too slow to be safe, way too slow to be useful. So this is where our story gets its hero. A group of researchers came along with a new idea, a new architecture they called SSD. It stands for Single Shot Detector. And that name, well, it gives you a huge hint about its genius. It was built from the ground up to just shatter this speed versus accuracy problem. So how'd they do it? Well, the older methods, like that super accurate faster RCNN, they worked in stages. First, they'd kind of guess a bunch of spots in the image where an object might be. Then they'd run a check on each of those spots. It worked, sure, but that whole multi-step process is what made it so slow. SSD's big idea was to just get rid of all that. It looks at the image just one time, in a single shot, and figures out everything it needs to know all at once. But wait, how can it possibly find everything in just one pass? This is where the real magic happens. It wasn't just one simple trick. It was a combo of two incredibly smart innovations that let SSD be both crazy fast and super accurate. Let's take a look at how they pulled it off. All right, the two big ideas are called multi-scale feature maps and default boxes. These two concepts work together, and they're what let the network find objects of all different shapes and sizes, all at the same time, without needing that slow, separate guessing step. Okay, let's break down that first one, default boxes. It sounds a little technical, but the idea is actually super intuitive. Imagine you're trying to find things in a picture. Instead of starting from scratch, what if you had a set of stencils in different shapes and sizes? A tall, skinny one for a person, a wide, short one for a car. SSD does basically that. It has a whole set of these predefined default boxes, and its job isn't to draw a box from nothing, but to just nudge and stretch these smart stencils so they fit perfectly over the objects it finds. It's way, way more efficient. Now, the second innovation, multi-scale feature maps, solves another huge problem. How do you find both a tiny little cat and a huge bus in the same go? Well, instead of looking at the picture at just one resolution, SSD creates a bunch of different versions of it, from super high res to pretty low res. It's kind of like looking at the image through a whole set of different magnifying glasses, all at the same time. The high res views, they're perfect for spotting tiny details. And the low res views, they're great for finding the big, obvious stuff. It's scanning for everything, at every size, all at once. And this right here illustrates that perfectly. On the left, the network is using its high-resolution maps to lock onto that pretty small cat on the desk. But on the right, it's using the lower-resolution maps to spot the big cows out in the field. It doesn't have to choose. It gets the best of both worlds inside a single network. Okay, the theory sounds awesome. A single shot, smart stencils, multiple scales. But did it actually work? When the rubber met the road, how did SSD stack up against the models that forced that awful choice between speed and accuracy? And wow, the results are just dramatic. I mean, look at this. Faster RCNN was chugging along at 7 FPS. YOLO was way better at 45. But then SSD comes in at a blistering 59 frames per second. That is a massive leap in performance, putting it solidly in the real-time category. But here's the real kicker. It got that incredible speed without sacrificing accuracy. The authors say it right in their paper. SSD is not just faster, it's as accurate as slower techniques like faster RCNN. It didn't just bend the rules of that trade-off, it completely broke them. For the first time, you could actually have both. And it wasn't just a one-trick pony. SSD proved to be unbelievably versatile. It could handle all sorts of different scenes with ease. It works just as well spotting big cows in a field as it does tracking lots of smaller moving objects, like cars and traffic cones in a busy city. I mean, it can find a pizza on a table and then just as easily it can break down a complicated living room, pointing out the chairs, the couch, the TV, all at once. This kind of robustness is exactly what you need for something to work in the real world. So, a faster, more accurate algorithm is awesome for researchers, but why should the rest of us care? What does a breakthrough like this actually mean for our everyday lives? Well, real-time object detection is the key that unlocks so much of the future we're always hearing about. It's what lets a self-driving car's brain process the world around it in an instant. It's the tech behind security cameras that can automatically spot an emergency as it's happening. It powers those fun augmented reality apps and gives robots in factories the ability to see and interact with their environment safely. So in the end, SSD and this whole single-shot philosophy, it wasn't just a small improvement. It was a huge fundamental shift. It's what helped pull AI out of the research lab and put it into the real, messy, fast-moving world that we all live in. It made AI practical. A leap forward like this just opens up a whole universe of possibilities. It really makes you wonder, right? Now that our machines can finally see and understand the world at the same speed we do, what incredible things are they going to help us see next?